going on, everybody? I'm Luke Calgary, part of 6th period chemistry for Mr. Buchanan. In today's episode, I'll be discussing my knowledge and mastery of our first unit about wildfires. So, if you're not familiar with wildfires, here's a quick definition. A wildfire is defined as an uncontrolled fire burning through combustible vegetation in an open area such as forests, croplands, or grasslands. In order for a wildfire to start, there are three components necessary. This model right here is what we call the fire triangle, which illustrates the three elements a fire needs to ignite: fuel, heat, and oxygen. With respect to those three components, there are two specific ways to contain a fire. You can take out a fire aerially with a mixture by the name of slurry, or flanking, where firefighters start on the perimeter and work their way to the core using water. Being a citizen of California makes me want to stay more in the loop of wildfires, as wildfires impact our lives in California more regularly than other states. As you can see, here's a graph representing how the number of fires change over time in the US, and another graph representing the number of acres affected by wildfires in the US. Both of these graphs consist of the same independent variable on the x-axis, which is a date ranging from 1983 to 2019. These representations are important to understand because the number of wildfires started off at a low rate around 1983, but quickly increased exponentially, staying moderate after the 2000s. This leads us to our first big question of why have wildfires in California become more destructive over the years. We know wildfires are becoming larger in size and more frequent in occurrence, but why is that? According to editors of the Union of Concerned Scientists, wildfires in the western US are getting much worse. While the fire is an essential and natural part of these ecosystems, warming temperatures and drier soils, both tied to human-caused climate change, have contributed to observed increases in wildfire activity. More specifically, in California, like much of the West, gets most of its moisture in the fall and winter. But while California has always been fire-prone, the link between climate change and bigger fires is impossible to separate. Second question. What are the benefits and consequences of a forest fire? This is a great question to look at because although fires have devastating consequences such as homes being destroyed, an increase in carbon dioxide levels that travel into the atmosphere, and ashes destroying many plants and soil's nutrients, it sucks. But there are, believe it or not, a few benefits from a forest fire. Forest fires remove low-growing underbrush, cleans the forest floor of debris, opens the tree to sunlight, and helps nourish the soil. Reducing this competition for nutrients allows established trees to grow stronger and healthier. These outcomes can be from controlled burns, which are intentional burns for forest management. Third question. What is combustion? Alright, now that you're probably familiar with the causes and effects of wildfires and just the overall details about the topic, I'd like to move on to sort of the science aspects that are involved in wildfires. One word that you'll most likely hear a lot when talking about this component of wildfires is the word combustion. Yep, you heard it. Combustion is basically the process of burning something, which in this case is wood from forest trees. And fire is a product of combustion, which is started from the three elements I mentioned earlier, which are heat, oxygen, and fuel. There are many everyday examples of combustion that you're probably familiar with. For instance, a lighted match, burning coal, or even fireworks. Fourth question. Model the atoms of the combustion of a fuel to show conservation of mass. Alright, now let's transition to the law of conservation of mass and how it can apply to the combustion of a fuel while its atoms are burning. Here's a quick definition of the law of conservation of mass. So the law of conservation of mass states that for any closed system, the mass of the system must remain constant. So in other words, mass cannot be created nor destroyed. So as you can see, this is a model I drew up showing the combustion of wood burning. There are the reactants on the left and products on the right. For the reactant side, there's wood that has burnt oxygen, and those add up to the mass of wood and oxygen. Those both yield to ashes, carbon dioxide gas, and water vapor, serving as the products, and those are mass of ashes, carbon dioxide, and water. So as you can see, since the reaction is performed in an open system, the mass of gases that escape also count. The same experiment can be performed in a closed system and relate to the results of the open system. In both, the law of conservation of mass is followed, where mass is neither created nor destroyed, but instead yielding to the components. Fifth question. Show a calculation of how the heat released during combustion can be quantified using numbers. During the first unit of chemistry, we completed a lab called the Combustion of Fuels, and in this lab, we found out how heat was released during combustion and the necessary calculations to find this out. Right here are 2 of the 5 fuels we studied and took notes on during this lab. In order to find the amount of heat release for the first fuel, pentanol, we'd solve to get the heat release by using this equation right here. The Q represents the changes in thermal energy, the M represents the mass of the substance, the T represents the change in temperature, and the Cp represents the specific heat of a substance. For the data I received, my next step would be multiplying all these numbers, getting a number of 15,325.992, which is 1.5 times 10 to the 4th power joules in scientific notation. But I'd use this original number, divide by 0.388 grams, which is the mass of the fuel combusted, and get a number of 39,497.4227, which rounded to 39,500 joules over grams. For methanol, I'd end up using the same formula to calculate the changes in thermal energy and go through the same process I did with pentanol. And my end result was 13,684 joules over grams. 6th question. Describe wildfires showing the difference between qualitative and quantitative observations reported by fire scientists. If you're not familiar with what a qualitative or quantitative observation is, it's simple. Qualitative observations are more observable data that might use your sense of sight, smell, taste, touch, and hearing, while on the other hand, quantitative observations refer to more numbers and can be observations made with objects like rulers or graduated cylinders. Some qualitative observations of wildfires are their blazing orange look, smoke affecting people's lungs, and the sound of shrubs and other debris burning. On the other hand, some quantitative observations of wildfires are the number of how many acres burned and the distance smoke travels. Alright, thanks for tuning in to this little segment on everything wildfire related. Hopefully you learned something. If you didn't, I don't know what to say, but let's hope you did. And until next time, peace!